In this video, we are going to now take a look at another factor that can affect equilibrium, or rather that can shift an equilibrium. In the last video, we saw temperature and we saw also concentration changes. Here we're going to see a factor that affects only gas systems. So only gas systems, and this factor is changing the pressure via the volume. So just a little reminder, when you are, let's say you're increasing your volume, that means you have more space, your pressure is decreasing. And when you are decreasing your volume, that means you have less space, so your pressure is increasing. And in general, pressure is basically particles hitting the walls of a container and hitting each other. And so what that means is that generally the more particles you have, so more particles or more molecules, the higher the pressure will be, especially if they're crammed in a small volume of space. So more particles generally leads to more pressure for a given volume of space. So let's go and take a look at our gas system we had here. Earlier we had X gas plus Y gas produces Z gas. And then there's also some heat, but we don't worry about that right now. This is just the same system we're working with before. And again, this is what we're going to do in this case is we're going to apply a stress, and the stress is going to be to reduce the volume. And so by reducing volume, remember that we're increasing the pressure. So we are increasing the pressure because there's less space now. And we want to think about what we're doing here. We're increasing the pressure. So what does the system want to do? Well, automatically it wants to reduce the pressure to counteract that. So to reduce the pressure, we need to think about what we need to, in terms of our reaction. Do we want to shift to the right, or do we want to shift to the left? B. And so our goal is to reduce pressure, and to reduce pressure, we have to look at the number of particles. So let's analyze the number of particles on both the reactant side and the product side. On the reactant side, all you have to do is count the coefficients, add them up, and that's the number of particles. So on the reactant side, I have 2 particles, right? 1 and 1. This makes 2 particles. Whereas on the product side, on the right side here, I have only 1 particle. And so there's fewer particles on the right side. So if I want to lower pressure, I want to get a smaller number of particles. And so the best way to do that is to go from my left side, where there's 2 particles, to my right side, where there's only 1 particle. And that should reduce the pressure overall. So what would that look like? So here we have again our graph of time versus concentration. And we've reached equilibrium at this point here earlier. So that's the initial equilibrium that we've reached. And we're all happy. Let's call this the old equilibrium because it'll change eventually. We're nice and stable here and here and here. Concentrations aren't changing because we're at equilibrium. But then all of a sudden, I add a stress at this point here. And this stress that I've added is an increase in pressure. So here's the interesting thing. When you increase the pressure, you're initially going to see a jump in concentration for all the gases in the system. That's because the entire system is being affected by that pressure change. So if you've increased the pressure, you have a smaller volume of space. So what that means is that you have a higher concentration of your gases. So you'll see this sharp increase immediately for all of the entities in the reaction, as long as they're all gases, which is different from when you were adding. When you were adding something, the only thing that saw a sharp increase was the one that you added for specifically. So just the X, for example. And temperature, well, none of them saw a sharp increase. But when you have an increase in pressure, all of them see a sharp increase at the onset, so immediately. And then afterwards, things can decrease or increase as needed. If we saw an increase in volume or decrease in pressure, then we would initially see a sharp drop for all of them. But at this point, we see a sharp increase since we increase pressure. And now what's going to happen is we're going towards the right side to reduce the amount of particles. So that means we're using up X and Y. So we're going to see a drop, and then it stops dropping, a drop, and then it stops dropping. But then for Z, it's going to go up, and then it stops going up. And so essentially at that point where they've all flatlined, this is our new equilibrium. with the same K as the old one. So the K for this type of effect is constant. Will be at new concentration values, but when we take the ratios in our equilibrium expression, the K will be constant at the end. So really, so far, the only thing we've seen that changes K is a change in temperature, because it affects the forward and reverse reaction in different ways. Since we have endo versus exothermic, they're different with respect to the different directions. So what is a generalization that we typically see here? So when it comes to the change in pressure by the effect of volume, we find that the shift occurs to reduce the number of molecules. That's if the pressure went up, because you want to reduce the number of molecules to lower pressure, or increase number of molecules, and that's if pressure went down. Because if pressure goes down, you want to increase the pressure again, so you need more molecules to do that. So suppose I had a decrease in pressure here, then my best bet would be, my best action would be to go from Z to XY to get more particles if I reduced pressure overall by increasing volume. So that was the other factor that affected that shifted equilibria from left to right or right to left. And now you know how to predict which direction it would go when you see an increase or decrease in pressure by affecting the volume. In the next video, we'll see two more factors that we sometimes apply to systems, but they actually don't have an effect in terms of the shift for an equilibrium.